About 4.6 billion years ago, on the edge of a spiral arm of a pretty obscure galaxy, a lot of space rubble starts circling in a slow gravitational dance. These rocks and gas are the remains of several stars that exploded long ago. Perhaps about 100 million years later, this space junk begins to collect together under the force of gravity, lighting up from the energy of spectacular collisions. Planetoids smash into one another, causing some to shatter, others to merge. One planetoid will become the Earth. It suffers constant, cataclysmic bombardment and swells into a glowing molten ball. About 100 million years after the Earth began to form, a change, lava, literally the scum of the Earth at the time, the lightest part of the molten magma sphere, begins to cool and darken into a crust. For now, the crust will keep melting, but it's a start. Then something truly remarkable emerges. Lighter blobs of the molten Earth called cratons shoot to the surface and stick, giving rise to the beginnings of the Earth's permanent crust. Meanwhile, the lava of the primordial Earth's surface has been belching out water vapor and other gases. Eventually, the atmosphere gets so saturated with water vapor that it begins to rain in a continual downpour that drenches the lava for as much as 1 million years. Flying past the Earth at this time, we see a vast gray ocean beneath a red-tinted sky, punctuated by volcanoes and small land masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, two cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in. It's going to be a bumpy ride. Here's how it might have happened. At first, Cratons and one continent called had the planet all to themselves. Then, around 500 million years later, Antarctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Antarctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the three landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close. Run the Earth time machine backwards, and you can see why. But no matter how many times you run the demolition derby of the continents, a question remains. What the hell is driving them? hell, apparently. The force driving the plates is the slow movement of the super-hot semi-solid mantle that lies below the rigid plates. Like hot soup, magma boils in slow motion. Superheated magma rises to the surface, begins to cool, and then sinks back down to the bottom of the pot, where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell, or convective flow. But where's the heat source keeping our earthy soup performing its circular gymnastics? Well, most of it is left over from the spectacularly energetic collisions and gravitational crushing that created the Earth to begin with. It's still trapped down there, and it wants out. And there's something else in the molten depths that makes it pretty hot real estate. Radioactive material. The belly of the beast has plenty of uranium and other radioactive elements, all of which release heat as they decay. That decay has significantly slowed the rate at which the Earth is cooling. So what does this mean at the surface? Two things. First, magma being burped up along the ridges, those places like Iceland where the Earth is tearing itself asunder, is pushing the plates in their respective continents apart. Second, what goes on at the other end of those plates, the collision zone, may be equally important. Here, where the heavier plates dive under the lighter ones, yanked downwards by gravity, they haul along their plates back into the oblivion of the mantle. That's what we know, or what we think we know. But the details of what's going on in the deepest parts of the Earth that drive the engine of plate tectonics, we may never know. But what practically all scientists agree on today is that virtually everything on our planet is being shaped by plate tectonics, including the grand panorama of life itself. The Himalaya majestically lay claim to 96 of the 100 tallest mountains on Earth. And Everest, the highest of all, pokes a hole in the sky at 29,000 feet. High up on Everest, higher than the saner among us dare to go, you can find something fascinating: fossils. Fossils of sea creatures from the trilobite family. Some more than 500 million years old. How did they end up at the cruising altitude of an airliner? This dramatic episode of Earth's soap opera might be called When Continents Collide, and the result gives new meaning to the term upward mobility. Let's rewind Earth's history by about 175 million years. Something that looks suspiciously like India breaks off the southeastern tip of Africa and begins drifting north. Then, 50 million years ago, boom, the leading edge of the Indian plate, which is oceanic crust, slams into the continental Eurasian plate. When the two continents meet head-on, the crust buckles upwards. The Eurasian plate crumples over the Indian plate. The collision of the two plates over millions of years has thrust the Himalaya and the Tibetan Plateau to their present dizzying heights. And they're still growing. Where they will stop, no one knows. Global positioning devices planted on the summit show that Everest seems to be rising by 1.5 inches a year. And that's how those little ocean-loving trilobites got all the way up there. They used to live in the sea that India squeezed shut just before it rammed into Asia. So much for when continents collide. But this is only the tip of the iceberg of our journey through earthly collisions. Sometimes continental plates smash into ocean floor plates. Sometimes seafloor hits seafloor. And sometimes plates simply grind against each other, like ships passing way too closely in the night. all to create topography as awesome as Mount Everest is tall. When the lighter continental plates crash into the heavier plates of the ocean floor plunges underneath, creating the very deepest parts of the oceans, its trenches.